Morning, everyone. So I was thinking it would be good for review if we just had another look at some of the PowerPoint slides that we looked at through this option here. Again, these slides here were designed by a teacher in enrichment, Mr. Eastwood, so definitely credit to him. Hopefully, as we look through this PowerPoint, it'll review with you some of the major topics that we covered in this option. It may be actually useful for you even starting off in this option here, just getting a sense of what we're going to be looking at in this module here and seeing whether you want to study this for your option. So this one here is option C on energy. We started off here with section C1 on energy sources. Our first big idea here is when we looked at our energy sources, for an energy source to be useful, it has to be able to release our energy at a reasonable rate, not too fast, not too slow. We also need to be able to harness it in a safe enough fashion as well. And another benefit is if in using these energy sources, it also produces minimal pollution. So starting off here, let's take a look at just in our world, what are some useful energy sources? We're going to look at burning fossil fuels, so burning gasoline in our cars. We're going to be looking at nuclear energy and fission style reactors. We're going to be looking at harnessing solar energy and electric energy. These are all useful energy sources that are able to deliver energy at a quick enough rate to be used safely. Some of them, unfortunately, cause some environmental impacts. Let's say burning fossil fuels, it tends to release a lot of carbon dioxide and other potential global warming gases that have greenhouse effect. So maybe the minimal pollution factor is not as good, but the reason why we have such a heavy dependence on fossil fuels at the moment is because it's such a good high energy source here that we can utilize for our day-to-day dealings. So second feature here is a reasonable rate. It has to be not too fast, not too slow. For example, we talked about rainwater. Rainwater here does have a lot of gravitational energy. The clouds are very, very high up in the sky. However, when those rain droplets actually fall to the earth, it's actually not releasing that stored energy at a quick enough rate. What I can do is I can actually build up, let's say, a dam. I can store up all the rainwater, and I can actually control how quickly that water actually flows at. That's actually going to be a nice alternative source here with hydroelectricity. It provides it with a lot more at a reasonable rate. Nuclear energy sources, we're going to see they have a lot of good advantages. We don't need a lot of fuel in terms of amounts. However, many times for a nuclear reaction, the reactions themselves are chained to one another. So basically, it's very easy for them to spiral out of control. We have some sad stories of when nuclear power plants had meltdowns, things like that. We need to make sure these useful energy sources are not only providing the energy we need to be able to harness it safely as well. So think right here in our kinetics chapter, if it is a chemical reaction, what are the things that attribute to activation barrier? Are there anything that we can tweak in terms of concentration, temperature, pressure, volume, adding catalyst to things? How can we actually control the rate so it's not too fast, not too slow? The other feature, like we mentioned, is if it can produce minimal pollution. We are going to look at molecules like CO2. First thing to be careful is CO2 and water are natural gases. We do need some measure of warming of the Earth. It allows it to keep the Earth's average temperature around 10 degrees, 15 degrees or so. Were it not for any greenhouse effect or global warming, the Earth would be way too cold to actually sustain life. So we need to worry about sort of having enough CO2. I guess the concern is because we're burning so many fossil fuels, we're producing artificially way more CO2 in the atmosphere than there otherwise would be. So just a generic thought just to think about here, which is a more useful energy source, a AAA battery or a voltaic cell like the one that we built in a redox unit? So if you imagine a AAA battery here, first thing I would say the states are a little bit better for a AAA battery. Instead of actually having aqueous and actually liquids that if I topple the voltaic cell, if I sort of angle it in different orientation, maybe the electrolytes here can't contact the electroplates. The AAA battery would typically have a moist paste for the electrolyte material so that if you put the AAA battery standing upright or on the side here, it'd still function. AAA batteries, some of them can be designed as rechargeable, so that's another advantage over a voltaic cell. A voltaic cell, once the chemicals runs out, it's out. We're going to call those voltaic cells here primary cells here. They're able to deliver a lot of energy, but again, the downside is not all of them can actually be reversed, whereas some AAA batteries, we can basically plug into a wall socket, we can actually recharge the battery, we can actually reverse some of the reactions and allow the battery to actually discharge again. The second big idea that we looked at in this section is, although the quantity of energy is always conserved, right? We have energy in is equal to energy out. You can't create or destroy energy. Energy can be transformed and passed between object to object. We talked about this notion here of quality of energy. The quality of energy is actually steadily being degraded because there's always going to be heat transfer to the surroundings. Every time I convert energy from one form to the other, I'm always fighting this losing battle. This is guaranteed by the second law of thermodynamics. The entropy is always increasing. We always lose some of the energy to the surroundings, and therefore we're going from energy in a concentrated, useful form to a more dispersed form that's no longer as available for work anymore. Although the quantity doesn't change, the quality of it decreases. So in this case here, quality matters. How come then we rely on non-renewable sources like fossil fuels so heavily? Again, they are very high energy molecules there. They're called renewable because they took millions and millions of years to form. However, the high energy that we get from actually burning these sugars here are able to provide energy to run our cars, run our electrical needs, things like that. That's why currently we have such a high dependence on fossil fuels. There's a increasing push towards trying to use some more renewable sources. So going from non-renewable sources, renewable sources would be things like hydropower, thermal energy, solar energy here, things that can be replenished within our time span. Not necessarily overnight, but for example, if I use solar panels, the sun pretty much is the ultimate energy source here. I can run it for as long as I want. It doesn't rely on waiting millions of years for these fossil fuels to actually form the coal deposits that we need. So for a renewable energy source here, we talk about these energy sources being naturally replenished within our time scale. It shouldn't take millions and millions of years like the fossil fuels. Although we do have a vast supply of these non-renewable sources here, they ultimately are finite and they eventually will run out, and then we'll have a problem with how do we get our energy needs then. We're going to start off looking at our first non-renewable source here. In fact, all fossil fuels here, they took millions and millions of years to actually form. Fossil fuels in general were formed from the reduction of biological compounds. So if you can imagine either land creatures or marine creatures, they're organic in structure, so they are built up of carbons, hydrogens, nitrogens, a bunch of the common organic elements. Over time here, they end up getting reduced. They end up losing hydrogens, end up losing elements. We find that they actually lose oxygen quicker than the other ones. So typically, what would have otherwise been nice high-energy sugars and living molecules here end up forming hydrocarbons, which can be harnessed in this section here for burning fossil fuels. So they contrast two primary fossil fuels. One is coal. The way I picture it here is we're thinking terrestrial. We're thinking land-based plants, land-based creatures here. They get buried over with lots of dirt here, maybe underwater, over millions and millions of years. And under that high pressure, high temperature here, it ends up forming coal deposits. But that ends up requiring millions and millions of years. If you contrast that with petroleum products here, petroleum instead of terrestrial plants here, we look more so at oceanic creatures here, oceanic plants here. They also die off. They're also at the bottom of this ocean here. They get put under high temperature and high pressure. And in that sense there, we can design these sort of underwater factories where we basically do really deep sea drilling and we actually can harness some of that petroleum for natural gas. The only problem here is when I actually take this coal or take this petroleum out of the ground, the petroleum is actually a big mix of a bunch of hydrocarbons. What I need to do is I need to separate them depending on my particular use. So the main way that we did this, running it through a fractionating column. So we're using a physical technique of distillation. We're using the fact that they have different boiling points to actually separate one layer from the other. So imagine digging up this crude oil here. It's a huge mixture of these reduced hydrocarbons, C and H compounds. Some of them range from C1s all the way up to C200s. They can be long chains, they can be branched, a lot of different isomers. A lot of the larger molecules are not very useful. So what we're going to do here is we're going to treat them. First thing that we do in this fractionating column here is we actually heat all of them. Usually we throw around a number of about 400 degrees, 500 degrees. That's hot enough to vaporize all of them. For these hydrocarbons here, because hydrocarbons here have nonpolar chains, we know that they rely just on those weak London forces to hold them together. That's why we don't need such intense temperatures. However, what's going to happen here is that heat source here is near the bottom here. as we compare sort of the really long chains to the really short chains here, the longer chains here would have more charges. More charges means stronger London forces, and being stronger London forces, we'd expect them to have higher boiling point. So although all of them have been vaporized, all of them have been put in the gas state before being shunted into this column here, the heavier gases, the one that have the highest boiling points, are the first ones to actually condense. We can actually condense them and taper them off in different layers, and we can actually fractionate them based on the different carbon lengths. So we heat them all. They rise up this tall column here. Just keep in mind here, the heat source here is at the bottom. And then what's going to happen here is the longest chain are going to condense at the lowest layers because they have the highest boiling points, the strongest London forces, whereas the shortest chains here, in fact, C1 and C4, even at room temperature, they're still gases, but steadily here we have the boiling point here gradually decrease, and we can slowly taper them off here. We can basically utilize them for the different uses that we need. So why do shorter chains rise higher is because they have weaker London forces, and they actually are able to stay gassed for longer, being away from the heat source. Primarily what we're interested in is these sort of C5s to C12s or so. This runs our everyday needs, like our gasoline engines, maybe diesel fuel for planes, things like that. Unfortunately, if you just take crude oil, if you just run it through this fraction, separating them by different boiling point, we don't actually manage to have a lot of them there. So separating them into different fractions is good. It's able to give me some of the length chains that I want, but what we're going to actually want to do is we will actually want to increase that supply. We're going to see in the next couple slides here, one main technique is to take some of these heavier ones here. If I can't utilize them directly, I can run them through a process called cracking. Cracking involves taking a longer chain, breaking them up into a smaller chain, or somehow taking these smaller chains here, almost like an addition reaction, forming them into more of those C5 to C10 that I actually want. Specifically looking at a gasoline engine here, we take a look at the different fuels that we can use. There's a very common feature called knocking, where the engine actually literally makes a knocking sound, and it basically is related to when I'm burning the fuel quality is actually not as good, and this knocking is actually this tendency to auto-ignite. The fuel is supposed to be sparked from your spark plugs from your cars. It's supposed to be burned when your pistons are sort of maximally engaged. In this case here, because the fuel itself is so easy to burn, even as your pistons here may not have fully reached full volume yet before it starts burning, it might actually auto-ignite, it might actually burn too quickly, and therefore we're not actually supplying that burning, we're not actually releasing that energy at exactly the right rate that your engines have been designed at. So what we do is we create a feature called Octane number. When you go to a gasoline station here, we actually have these rated as Octane number. The higher the Octane number, the better quality the fuel itself is. So more on this Octane number feature here. Fuels burn very efficiently when they're supplied with the correct amount of oxygen. You can think about the stoichiometry from the balance equation here. Whatever mole ratio is set from the balancing here, that's the amount of oxygen that we wanted. If we have too little oxygen, we have what's referred to as a rich fuel-to-air mixture. We have too much fuel, not enough oxygen. In this case here, not enough oxygen results in something called incomplete combustion, partial combustion. And partial combustion, instead of fully oxidizing and getting fully CO2 and fully water, we end up getting carbons and carbon monoxides. That carbon here is unburned soot. It's going to typically be solid, and it typically amounts to a very darker and dirtier flame. If I have too much oxygen, not good as well. In that case there, we refer to this as a lean fuel-to-air mixture. In this case here, we don't have enough fuel. It's sort of being snuffed out by too much oxygen. And in this case here, it causes the fuel to burn at a rate that I don't want. And it, in this section here, is called knocking. So for octane number here, some generalizations. Straight chain hydrocarbons are very prone to knocking. So these ones here are not really good quality fuels. Whereas if I can increase the branching, it's more resistant to knocking. So as I define this octane number rating here, it's found experimentally heptane, a 7-carbon straight chain molecule here. It's really high tendency to knock. We call the an octane number of 0, versus another compound here, shorter chain here with a lot of branching here. This is going to be my standard reference. We can call it isooctane. It actually in reality is 2,2,4-trimethylpentane. It's a 5-carbon chain with a bunch of branches. This one is known to burn really well. This has an octane rating of 100. So when you go to a gas station and I get, let's say, 91 gas, that fuel that I'm putting in, it's not actually made out of real heptane or real isooctane. But if I had a mix, 91 octane, it's a mix of 91% isooctane, 9% heptane. It burns like that mixture. Again, the fuel itself does not necessarily itself need to be heptane or isooctane, but it burns as if it was made from a mixture or proportion of this much isooctane and this much heptane. What we're going to do here to try to increase the octane number is we're going to try to increase the branching, shorten the chains to the length that I want it, so we can deal with cracking and reforming as two common chemical techniques to not only get the short chains that I want, but to change the molecular structure so that the fuel itself burns better. At a high temperature, we can crack a long hydrocarbon chain. These ones here won't climb as far up the fractionating column here. Anytime you do cracking here, we're going to break an alkane, a single bonded saturated molecule here. We will always only get one alkane, and the remaining of them are going to be alkenes. I do a derivation in this option here to show you we actually don't have enough hydrogens to actually create more than one alkene. So cracking, yes, it involves breaking something long and making something shorter. We're always going to get one alkane and any number of alkenes. So if you're curious, you need to look back into that section. We just don't have enough hydrogens to make two alkenes. In terms of cracking here, we have a couple different styles. We can do what's called thermal cracking, basically a heat treatment. We also typically couple it with high pressures, so 100 times the normal atmosphere that we're at. We can do steam cracking, so under the presence of just water as gas. Or we can perform what's called catalytic cracking here. Catalysts, we know in general, they lower the activation barrier. They allow the reaction to occur at a lot faster rate. We mainly looked at zeolites as catalysts. Zeolites are naturally occurring minerals that are sort of oxides of aluminum and silicon. These ones here can actually control how the reforming process actually works out. So you can imagine here, after fractionating the crude oil, we now have a couple different layers, mixtures of chain lengths here. Let's say this is the C5 to C10 that I wanted here. Unfortunately, out of that typically comes a lot of straight chain alkanes. If I can somehow isomerize it over that zeolite, if I can actually break apart them and reattach them, I can actually form structural isomers. So in this case here, I now have a mix, some straight, some branched chains here. I can try to separate off the branched ones. Even though their sizes are very similar, the more branching they has, it sort of hides away some of their internal molecules there. I would assume that the London forces are actually weaker the more branching that we have. So based on that feature here, we might be able to separate them. If they're not quite separated, I can just shunt them through again, and I can just continue reforming them, continue to increase the branching. Other types of reforming that we can do is called cyclization. So I can take a straight chain alkane here, I can end up forming a ring. There's our sort of aluminum platinum catalyst again. This has to be high temperature, high pressure. I can even make aromatic compounds, rings, as well as if I can introduce multiple bonds here, it typically allows the octane number to go up as well. It produces a higher quality fuel. As we look back at coal, so coal primarily is just carbon. It's been concentrated to about maybe 80%, 90% or so. Although coal is a high energy molecule, the main disadvantage is we need large scale power plants to actually be able to extract the energy in a useful form. We can't actually stick a solid lump of coal into your car engine here. Although it is a high energy source here, there's no way for your car engine to actually burn it, to actually transfer the energy that we need in a quick enough fashion. So what we introduce here is there's a way to gasify coal, make coal carbon into a gas or into a liquid so that it's much more feasible for use in our engines. So for coal gasification here, we take our coal, which is just pure carbon, we treat it with water, and we end up producing a mixture of hydrogen and carbon monoxide. Careful, carbon monoxide is actually a toxic gas, so we want to be careful. We have some safeguards around there. This mixture here of CO and H2 is referred to as synthesis gas. We can actually run this as a fuel source as well. This is used as a precursor for a lot of other organic reactions as well. But what we're going to see here is the coal has been gasified. We put the carbon into a gas state, and I can then use this as a fuel for my engines or whatever other energy device. We can also liquefy it here. It's almost like taking that H2 and the CO that we created from earlier, had come from coal, and basically we're just piecing them together and forming alkane. There's a general formula for an alkane here. In this case here, it's been liquefied. For it to actually stay liquid, it's important for you to know that the N has to be bigger than 4. And in fact, C1 to C4, methane to butane, those ones, the London force are so weak, it still is gas at room temperature that hasn't quite been liquefied yet. Why are we interested in liquefying these fuels here is because liquids are easy to store, easy to transport. It makes it a very convenient fuel to actually work with. So we have these hydrocarbon fields here. We might need catalysts for them. There's some details that we looked at in their section. We also take a look at what's called our carbon footprint in thinking about sort of our environmental impact. We also need to worry about some greenhouse gases that, because of human activities, are reproducing way too much greenhouse gases that are absorbing some of the radiation from the sun and actually re-radiating back to the Earth's surface. So in this case here, carbon footprint is the unit is amounted to, it's the equivalent tons of carbon dioxide. This becomes a stoichiometry problem here that's being expressed per year. So that's your carbon footprint here. It's in this unit here, equivalent tons of carbon dioxide. Carbon dioxide is sort of set as our reference. Again, it's important to note water and carbon dioxide are naturally present. If carbon dioxide is a reference, it has a global warming potential. Your textbook calls it a greenhouse factor of 1. Every chemical is now in relation to carbon dioxide. So for example, water, our most abundant gas, our most common greenhouse gas here, one molecule of water actually has a global warming potential, greenhouse factor of 0.1, which means I need 10 water molecules to have the equivalent effect of having 10 CO2 molecules. Methane coming from intensive farming, I don't have a lot of them, but dollar for dollar, one methane molecule has the impact of 30 times the damaging effect of fossil fuel burning, and going up from there. CFCs here were used in a lot of old refrigerators. When we tossed out those refrigerators, some of those ended up going into the atmosphere. They end up forming chloride radicals. We saw in chapter 4, it ended up catalyzing a mechanism to destroy ozone. So that was another environmental feature. In this case here, we're worried more so of it absorbing solar radiation and re-radiating it back to the Earth's surface. So that one there is mainly looking at sort of fossil fuels or carbon footprint. This one here, it differs depending on sort of first world countries, third world countries as well. We see a sort of statistic here on our relative carbon footprint. In general, we want to be minimizing carbon footprint as best we can. The next energy source we looked at was nuclear power. We looked at fission and fusion in general. In this case here, we start off with fission, which takes heavy nuclei. Fission means breaking apart. We break them into smaller, simpler nuclei here. And in this case here, because of fission, it increases this feature here called the binding energy per nucleon. This binding energy is the amount of energy that if I take a bunch of the subatomic particles, the protons and neutrons, if I add up the masses, I realize that the masses of the Lego pieces are actually a little bit higher than the mass of the nucleus itself. So once the nucleus itself forms, some of that difference in mass, we call that a mass defect, actually gets converted over to binding energy. It's that little amount of energy that actually can be harnessed for our nuclear power plants. To make sure we can make a comparison between different elements, we don't just take the binding energy, we divide it by nucleons. Nucleons are particles of the nucleus, so protons and neutrons. So nuclei themselves are made out of positively charged protons as well as their neutrons. We know the positive protons, positives don't like each other. In fact, they're so closely squeezed together, how come our nuclei don't just spontaneously break apart? Those electrostatic repulsions are being fought against by what's called the strong nuclear force. The strong nuclear force is something that holds the nuclei together. It's something that acts between neighboring molecules. Strong nuclear force is blind to charge, so a neutron will attract a neutron will attract a proton, even a proton will attract a proton in terms of the strong nuclear force, and it's the contrast between nuclear force and the electrostatic repulsion that actually tells you whether the nuclei can stay together or not. Binding energy is this energy that I described it as the energy that was released when the nuclei forms, or you can actually input this energy here to break up the nucleus. We need to convert that energy back into that missing mass for our protons and neutrons. It's that energy I can harness for our chemical energy. The greater the binding energy, the more stable the nucleus. Remember, the lower the energy, the less can go wrong. So here, what they plot for you here is that average binding energy per nucleon. They divide it by how many total protons and neutrons, and they plot it against the nucleons again on this side here. What you'll notice here is the higher up on the chart here, we have increasing stability. The isotope here that actually has the highest binding energy per nucleon is actually iron-56. In fact, if I go from any elements, we have the small things on the left side, the big things on the right side. We're going to start off with heavy things like uranium. Because as I break them into lighter compounds, because the binding energy increases, the nuclei itself is more stable, any energy that gets released off of that can be harnessed for nuclear power. I can also do fusion reactions, take lighter things, join them, glue them together, and by gluing them together, much more dramatic increase in binding energy, lots of energy gets released as they steadily form iron-56. They don't fully need to get to iron-56, but the closer I get to iron-56, both fission and fusion end up releasing energy. So binding energy is related to this mass defect, the difference between the parts themselves, add up the protons and neutrons, minus once the nucleus itself is actually formed. So we knew of conservation of mass. Where did that extra mass go? If we say that the nucleus itself is actually lighter than the sum of the nucleons, we have to use here Einstein's famous equation. Sum of that mass is actually converted over to energy. It gets scaled through the speed of light. We did a few calculations in this section here. You could add electrons for convenience, but mainly we're looking at the nuclei itself. We're looking at adding protons and neutrons for the individual masses, and we're looking at comparing to the nuclei's mass itself. Looking more generally here, then if I have heavy things can undergo fission. Fission is breaking apart. The daughter isotopes of products will generally have higher binding energy, more stability than the uranium itself. So looking more so at a fission design, all of our power plants actually utilize fission. We haven't managed to harness fusion yet. But here's a fission reaction here. The reactive radioactive form of uranium is actually uranium-235. We fire a slow-moving neutron at it. We need sort of control rods and moderators to actually slow down the neutrons so that the uranium-235 has a chance to actually capture it. This one here actually forms an unstable nuclei, and this one here then starts decaying. Doesn't have to be two things, but what we're going to generally see here is when it actually breaks apart, typically it ends up actually releasing off more than the number of neutrons coming in. So one neutron triggered this reaction, it releases two. But what if those two neutrons then trigger another one? Those two produce two. This will very quickly spiral out of control. Again, we need control rods here, not just to slow down the neutrons to allow for a good chance of capture, a good chance for these neutrons to actually run to other uranium-235s. We want to control that sort of on average. It is just one neutron. Even if it then releases 2 or 3 neutrons here, we sort of soak up the extra neutrons and just one neutron goes to trigger the next reaction. We talk about this term here, critical mass, as the amount of uranium here that if I fire that one slow-moving neutron, the neutron that ends up getting released from that has a good chance of running into other neutrons. Again, if it's releasing 3, I want to absorb some of the other neutrons here so I can have a good control so that the reactions can be controlled at a safer rate, and I can then self-sustaining, we can then use this nuclear power plant. So if I take this uranium-235, one of the byproducts is going to be plutonium. The question here is, unfortunately, a lot of this waste here itself is actually radioactive. Can I actually utilize this for useful energy? Turns out another common design here for a power plant is actually a plutonium reactor. Plutonium is actually a waste product out of that first reaction with uranium-235. These are referred to as breeder reactors because these are a lot quicker. These ones here would take otherwise waste plutonium and also cause fission on this plutonium here. We can actually create it from the uranium-238 isotope as well. We can actually breed more nuclear fuel from otherwise waste material. As we start taking a look at uranium compounds here, again, just like coal, carbon solid wasn't easy to use in the solid state here, uranium by itself, elemental, is not very easy to use. For our nuclear power plants here, we typically run it through as a compound of UF6. So the uranium here, uranium has 2 common isotopes. Uranium-235 is the fissionable form, 238 is the non-fissionable form. Unfortunately, in our universe, the primary form here, 99% of it is the 238. What we need to do is we need to actually enrich, we need to actually select for the uranium-235 the form that actually can actually react. So what we're going to do is we're actually going to leverage a physical feature. We're going to run it through diffusion or effusion. We're going to find that the uranium-235, because it's a little bit lighter, it travels ever so slightly faster than the uranium-238. If I can put a semi-permeable membrane up, I can slowly select for the lighter one, or run it through a centrifuge. In both cases, I can enrich the fuel. I can convert it from the 238 over to the 235 form. In contrast here, they just compare it to a uranium oxide compound. So this really is an ionic compound. It's a huge lattice. It's crystalline. This one here won't be really useful to use. However, compared to the UF6 that we just talked about, this one here is covalent. We know it's octahedral, it's nonpolar. Even though it does have a really high molar mass, because the fluorines are really electronegative, these partial charges here provide a very negative outside. When this UF6 here gets close to another UF6 here, the London forces that are left over between nonpolar molecules are not that strong. So in fact, this one doesn't need that 2000 we saw earlier just to melt. This one, a little bit hotter than room temperature, has already sublimed solid over to gas. So looking more so at the enriching case here, taking uranium-235, this is the fissionable form. This is the form that is actually radioactive. The uranium-238 is not. So what we need to do is we need to enrich it. We need to select for the lighter type. We need to enrich it to about maybe 3%, 4% before it's actually useful for us. One way to do this enriching here, like we mentioned, is setting up a membrane. We're going to rely on a guy called Graham's law. I do a derivation in this option here to say it's actually the inverse to their masses. It diffuses, it spreads out. Because the uranium-235 is a little bit lighter, it's going to move ever so slightly faster. So we do that math there. It's not by much. The time ratio that it actually, how much faster is the 235 is actually just 1.004. So what we can do is we can actually do this with the permeable membrane. We have uranium UF6 here. Some of them are UF6 with 238. Some of them are with the lighter 235. Because the 235, they diffuse and they effuse, they spread through these pores here ever so slightly faster, we're going to gradually select for more uranium-235. Just doing this once here will amount to 0.4% separation. Imagine though cascading this, running this one and then again and again and again, and over time we can steadily enriching this one here. Another way of doing this enriching is using a centrifuge, and we know for a centrifuge here, because of the centripetal force here, the heavy masses get thrown to the outside. UF6 based off the uranium-238 isotope gets thrown to a larger radius. If I can pump some of that out and I can actually just collect up the ones with smaller radius, collect up that's been enriched with uranium-235. This has to be done, like I said, multiple times here to actually enrich it enough that we can use as a useful fuel. There is a concern of it being utilized for nuclear weaponry, but in this case here, it would need to be enriched even more than what a power plant would need for weaponry. So at least for this uranium design here, we're not as concerned with this. What we are concerned, however, is some of the safety risks using nuclear power plants. It could be health effects, so it could be consequences damaging to our cell tissue. What do we do with the waste that itself happens to be very radioactive? If the reaction spiral out of control, we can risk meltdown here, and we can also risk, again, I mentioned the weaponry. So for health effects here, ionizing radiation, whether we look at alpha, beta, or gamma radiation here, those are high energy enough that can actually form ions interacting with your matter. So our primary body is made out of water. When it gets exposed to this radiation, it can actually ionize that water there. Those high energy ions and high energy electrons can go to damage our bodies. So some are reactions just showing you some other devastating molecules. So this is the ionization that I showed you here. Water can by itself be attacked by an electron, bombarded with this electron. We form this hydride radical as well as a hydroxide radical. These radicals with unpaired electrons we know are very quick. They're going to try to pair up with electrons and can be very damaging to, in this case, your DNA, proteins, lipids, a lot of what makes you who you are. There could be other radicals as well, so oxide radicals, superoxide radicals, all of them can be very devastating.